Hello, my name is Evelyn Moss, and this is my Physics 2112 Lab 2 on projectile motion. The purpose of this lab was to observe and analyze the motion of a projectile and compare it to a computational model with and without drag force. The fundamental physics principles in this lab would be Newton's second law on the momentum principle, gravitational force, and drag force. For Newton's second law on the momentum principle, net force is equal to the change in momentum over the change in time. This can be represented by the equation below, and we can see how the velocity update formula is derived from this by dividing by mass. Gravitational force is the attractive force that pulls objects with mass towards each other. On Earth, this is represented as Fg equals mg, where g equals 9.8 meters per second. Drag force is the resistive force that opposes the motion of objects moving throughout the air. The drag force equation is given below. The results of this lab will be that both the drag force and the non-drag force computational model, as well as the experimental model, were very similar due to the lack of air resistance in the environment. For the experimental portion of our model, the system was the paper ball, the surroundings were a table in the air, and the materials used to be a tape measure for calibration purposes and a camera to track the motion. For the experiment, we used Tracker to analyze the motion of a paper ball thrown like a projectile. The computational initial conditions are given as below. The mass was calculated using a digital scale, the initial position was measured with a tape measure, the initial velocity was found using an average velocity with the change in position over the change in time using the first two timestamps from the experimental data. Delta T is 1/30 because the video is filmed in 30 frames per second. The force of gravity follows the formula, and B is estimated off of our experimental data. For the computational model loop, the time is based on our experimental data. The second portion of the code calculates the drag force using the drag force formula with B from the initial conditions. The net force formula is then used, and then the velocity update formula is used, which is derived from the momentum principle. Position update is used next, using the new velocity to calculate a new position. And this loop will run until t is greater than 1/3, producing a comparable data set. Comparing drag versus no drag. With our drag force where b equals 0.001, and no drag force where b equals 0, the models are slightly different but very similar just because the difference between the b's is not that different. As for a comparison of the experimental values and computational values, because of this environment in which we filmed when the experiment took place, there was not much air resistance, leading to almost no deviation between the models with and without drag force. The model with no drag is still slightly higher in some spots and would be expected that in a longer model, greater deviation would occur. The experimental trajectory is broader than the computation models, and this is because of an error in calculating the initial velocity for the computation model. If there would have been no errors, the correct way the results should have been displayed would be with the experimental and the drag model closely modeling each other, and the no drag model slightly above. So now for some sources of error. Like I just mentioned, the initial velocity for the computational model was calculated using the average between the first two time intervals in the experimental data. The time intervals might have been too large to obtain a more accurate initial velocity. A human error also could have occurred when using Tracker. There is a chance that not all points of motion were directly centered on the paper ball. Now time for some final questions. The what does it mean questions is, do any of your models predict a terminal velocity? No, because velocity is still changing throughout, implying acceleration, as seen in the graphs below, meaning that the net force is not zero. To obtain terminal velocity, a longer experiment could take place where we measured a dropped object until observing a constant velocity. Lots of drag force would be required for this to occur, so maybe using something like a parachute could work. For the what-if question, it asks, if the ball was thrown straight up at the same initial velocity, would it take it longer to hit the floor of the table? It would take it longer for the ball to hit the table because it reached a higher peak and would then still have to fall to the table. Based on my calculations, it would be about 1.5 times longer to reach the ground, and the calculations I did to achieve the answer are listed below.